Hello everyone, I am Dr. Osman and today we are going to look at reaction independence. This is an issue that we have briefly touched on in previous examples where we had a reaction set of 3 reactions, however only 2 of the reactions were independent and so relevant for material balancing. And today we are going to look at a more rigorous approach on determining the reaction independence of each reaction in a reaction set. And once we can obtain our reaction or determine our reaction independence, then we can solve our material balances by drawing up a degree of freedom table and solving our balances as normal. Okay, so we'll look at reaction independence and how it fits into our calculation procedure. So let's get straight to it. Okay, you may recall that we've dealt with this reaction set before. However, let's just look at it again to revise. So we have 3 reactions occurring in one reactor, and we have 1-butene becoming cis-2-butene, cis-2-butene becoming trans-2-butene, and trans-2-butene becoming 1-butene again. And if we had to number these reactions, let's say 1, 2 and 3, then what we find is that if we, for example, add 1 plus 2, okay, reaction 1 plus reaction 2, we will end up getting 1-butene becoming trans 2-butene. Okay, so that's simply adding reaction 1 and 2. Of course, the cis-2-butene will cancel out. But now, as you can see, this reaction here looks exactly the same as this one here. Okay, especially since it's reversible. So, this reaction here, we can call it reaction 4. It's the same as reaction 3. If we add, for example, reaction 1 to reaction 3, we will get trans 2-butene becoming cis-2-butene. Okay, so the 1-butene from reaction 3 and reaction 1, if we add them together, then our 1-butene will disappear and we'll have the following, which of course looks exactly the same as reaction 2. So reaction 5 is essentially reaction 2. Okay, so something is fishy here. This does suggest that not all of our chemical reactions may be necessary. And another issue is that the above reactions are reversible. So it's essential to determine if our reaction sets contain independent reactions. Note that this is the actual chemistry of the reactor, right? These are the actual reactions that are occurring. But we want to know what are the independent reactions, because it is only the independent reactions that are relevant to our material balance purposes in order to obtain the amount of products, different products that are coming out of the reactor. Okay, so it's essential to figure out the number of independent chemical reactions because it reduces the complexity of the calculations, and also we have less variables, so it makes our mass balances solvable with fewer specifications. Okay, and that is ultimately a cost saving, because remember, the fewer the specifications, it ultimately means that the fewer the variables that we will physically need to measure. Okay, so we want to measure as little as possible and obtain whatever we can by calculation. Okay, so this is just the facts stated. Okay, so we need to determine if our reaction sets contain independent reactions. to reduce the complexity of the calculations and ultimately use less variables. And what we found previously, or what we've discussed, is that in the case of reversible reactions, a reverse reaction is simply a multiple of the forward reaction. So that is a dependent reaction, it's not independent. So if we look at our reaction set here, even though our reactions are reversible, in other words, we have theoretically 6 reactions occurring, our reverse reactions are simply multiples of our forward reactions. So we don't count our reverse reactions at all. And another basic rule from our previous examples is that if a reactant or even a product in a reaction set contains a species not present in other reactions, then that reaction is independent. Okay, so in other words, if I have, let's say for example, three reactions occurring in a reaction set, and if I have a single species that occurs in one reaction that doesn't occur at all in any of the other reactions, then that will tell me that that reaction is independent. Okay, and that species can be a product or a reactant as long as it is unique to a certain reaction. That will make the reaction independent. However, what if it's not so easy? What if I have a reaction set where all of my species occur in all of my reactions? Okay, so what do we do then? How do we establish independence then? So we are going to look at a more rigorous approach, okay, and that is the use of Gaussian reduction. Okay, so let's look at Gaussian reduction. You may have encountered Gaussian reduction in first year applied maths. So I'm just going to look at one example and you can revise on this technique in whichever way you can. Okay, so we're looking at Gaussian reduction of a matrix. Okay, to determine reaction independence. So I'm just going to talk arbitrarily for now. If you recall, we typically have a large matrix, and that matrix could have all kinds of numbers. Okay, and in the case of reactions, we can let our reactions be numbered. So let's say if I have my reaction 1, reaction 2, reaction 3 and reaction 4, and if I list my species here, okay, I'm just taking some random species here, I'm not looking at any particular reaction set. Okay, so in formulating our matrix, we write out our reaction numbers on the top and our species here, and these figures will be our stoichiometric coefficients. They are positive if we are looking at a product, if our particular species is a product, and negative if our species is a reactant. Okay, certain species may be positive in one reaction and negative in the other because they are being produced in one and being consumed in the other. Okay, and the aim of the game here will be to reduce this matrix to a particular form that looks like this. Okay, so this is what we would ideally want to achieve. We want to reduce this matrix that has lots of different numbers into a matrix that looks like this, where we have our ones diagonally across. Everything above our ones will be zeros, and anything below the ones could be any other number. Okay, that is the technique of Gaussian reduction. Okay, so all of these here are my stoichiometric coefficients. So let's look at an example of an actual reaction set. Okay, we're looking at uranium plus hydrochloric acid. Coming uranium chloride. That's our first reaction. Let's say, for example, in the same reactor we have zirconium reacting as well. And a third reaction. Okay, so just looking at this reaction, we note that we do have species that are present in our reactions that are not present in any of the others. Okay, so let me number this. Reaction 1, 2, and 3. So in this particular case, we have, for example, for reaction 1, we have uranium occurring as a reactant, and it doesn't occur in any of the other reactions. Therefore, we can assume that reaction 1 is independent. We have zirconium in the second reaction, which doesn't occur in any of the others. So the second reaction is also independent. And for our third reaction, we have our zirconium oxide, which doesn't occur in the other two. So we can also infer that the third reaction is independent. But how do we prove this mathematically in a rigorous method? Okay, so I've numbered my reactions 1, 2, and 3. And if I had to put all of my species in a matrix, okay, so I have 3 reactions, so the matrix will have 3 columns. And we'll look at all of our species that are occurring in these reactions. So we have to look at each species in all of our reactions. Okay, that's H2O, and then finally ZrO2. Okay, so let me just extend that. Okay, so how do we write out our coefficients? So let's look at the first reaction. We have uranium occurring as a reactant with a coefficient of 1. So in reaction 1 we are looking at a coefficient of -1. For HCl we have a 3, so that will be -3 for it being a reactant. We have UCl3 as a product, and finally hydrogen with a coefficient of 3/2. Okay, so none of the other species participate in reaction 1, so they all get a coefficient of 0. Let's look at reaction 2. Okay, so there's no uranium participating. However, we have 4 HCl being used up, no UCl3. We have 2 hydrogen being produced, and our Zr, zirconium, -1. Okay, so, oh yes, also the ZrCl4, that's a product, so that's a 1 as well. Okay, and no water and ZrO2 reacting in reaction 2. So let's look at reaction 3. Okay, using the same technique. These are non-participants. We have ZrCl4 being used up. We have water being used up, and ZrO2 being produced. Okay, so how do I reduce this matrix? Okay, so remember I need I need the matrix to look like this. So let me look at column reduction. A good start would be to multiply the entire column 1 or reaction 1 by -1, and that will make my matrix, this point here will be a 1, okay, which is what I am aiming for. So if I take reaction 1 multiplied by -1, okay, I want my column 2 to have a 1 at this particular position, so I can divide it by -4. Okay, that stays as 0. This is 1. Zero. That will be -1/2. This will be 1/4. Zero and 0. Okay, so column 1 and 2 seems to be looking more closely like this form here. However, as you can see, for our column 3 doesn't have any figure here, so I can't directly change it to a 1. However, I could add it to a multiple of the second column in order to get this 4 into a 0. Okay, so remember we want a form where we have our 1s coming diagonally and 0s above all of our 1s. So let's at least try to achieve that 4 changing to a 0. And we can do that by adding column 3 to a multiple of column 2, because we want to get rid of this 4, we need to add it to a negative 4. Okay, so we have to apply the calculation, of course, to the entire column. Okay, we're looking at column 2, the changed column 2 actually, not the previous column 2. So we are looking at this column here. And if we are comparing column 2 to column 3, so we have the old column 3, which is, so that's 0 plus minus 4 times the new column 2, so that will remain as 0. 4 plus 1 multiplied by negative 4, which is ultimately 4 minus 4, so that's a 0. 0 minus 4 times 0, that's also 0. And 0 plus negative 4 times negative half, so that will be a 2. And 0 times negative 4 times a quarter, so that will be a minus 1. And so on and so forth. Okay, so we have minus 1 times negative 4 times a quarter, so that's minus 1 plus 1, so that's a 0 as well. Minus 2 plus 0 times negative 4, so that remains as a minus 2. And this remains as a 1 as well. So note that in our attempts to change our matrix from this form to this form here, we ended up with this matrix here. And as you can see, all of our columns still look quite different. Okay, none of the columns look identical to each other, so all of them are regarded as independent. Okay, so no column has disappeared. Now if, for example, during our Gaussian reduction procedure, one of our columns ended up with all zeros, then it means that that particular reaction is not independent. So now that you know the basics of column reduction for our multiple reaction systems, let's look at a more comprehensive example. Okay, consider the steam reforming of methane to produce syngas. Okay, so if I have my CH4 coming in together with water and CO2, and it's being sent to a reformer, and at high temperatures we have the following reactions occurring. Okay, and the reformer output is also stated to contain a ratio of hydrogen to carbon monoxide of 2.2:1. Okay, so these are my outputs here. N2 of hydrogen divided by N2 of carbon monoxide is equal to 2.2. And we are also given a conversion of methane in the reformer to be 80%. Okay, and they want us to calculate the output composition. Okay, so they want us to calculate the composition of our product, and they have given us our feed composition. Now the immediate problem is the fact that our reaction set has 4 reactions. Also, what you will note about these reactions is that the same species occur at multiple reactions. So there is no reaction here that seems to have a species that is unique to that reaction. All of the reactions have all different kinds of species and they are not unique. Therefore, we have absolutely no option but to go for Gaussian reduction in order to check whether these reactions are independent or not. So that is our first step. Recall that previously for these types of problems, our first step would be to draw up a degree of freedom table. However, without knowing the number of independent reactions, we can't accurately write out a degree of freedom table. So therefore, from now on, when confronted with a problem like this with multiple reactions, your first step would be to determine reaction independence. Okay, so let's look at it. I can draw up a matrix. Okay, so let's number these reactions. Okay, it's just a simple 1, 2, 3, 4. And these reactions will be represented here. Now let's look at our species. We have to list every single species on our row. So let's start with our methane. Okay, then we also have CO2, we have CO, we have H2 and H2O. Okay, so across these 4 reactions, we only have 5 different species. Okay, so let's populate this matrix. For reaction 1, for CH4, so that will be a -1 stoichiometric coefficient. The same for CO2. CO is a product, so that's 2 there. And H2, that will be a 2 there. Water doesn't participate. So in reaction 2, we have no methane. CO2 is a product. CO in this case is a reactant. H2 is a product. And water is a reactant. If we look at reaction 3, we have -1 and there's no CO2. CO is a product, H2 is a product, and water is a reactant. Okay, for reaction 4, we have methane as a reactant, CO2 is a product, there's no CO, H2 is a product, and water is a reactant. Okay, and remember that in this particular case, and well, of course in all cases, we are looking at ideally having a matrix. Let's say for, okay, this is 5 rows and 4 columns. We ideally would want our matrix to look like this, right? So we can have any kind of number below the ones, but we must have ones coming across diagonally here and zeros above the ones. So this is what we are aiming for. So let's try and achieve this matrix. If we look at this current matrix now that we have drawn up, a good place to start would be to change this -1 into a +1. Okay, in order for the first row to look like this. In terms of column 2, it doesn't seem that we will need to do anything because we already have a 1 here and a 0 above the 1. These figures here can be anything. However, it seems that we will need to add column 3 and column 4 with a multiple of column 2 or perhaps even column 1. Okay, so let's get to it. Okay, so multiplying column 1 by -1, so that's quite easy. We don't need to do anything to column 2 at this point. I want this -1 in column 3 to be a 0. So I will need to add it to a multiple of column 1. Okay, so now we are performing an addition between column 3 from this matrix and our new column 1. Okay, and since we have a -1 here, if I simply add it to the 1 here, I will get 0. So let me apply that operation for the entire column 3. So I'm going to simply say column 3 plus column 1. So -1 plus 1, that will give me 0. 0 plus 1 will give me 1. 1 plus -2 will give me -1. 3 plus -2 will give me 1. And -1 plus 0 will give me -1. Okay, the same for column 4. I want this -1 to become a 0. Okay, I want it to look like this. Remember that when we are doing Gaussian reduction, we can only perform changes and make our zeros here first, and thereafter move on to column 2 and make these rows here 0. Okay, so even though I have a -1 here and a +1 here, I need to deal with this -1 first. Okay, so let's try and make this into a 0. And I can do the same thing. I can simply add column 4 to column 1. Okay, so that's -1 plus 1. That will give me 0. 1 plus 1 will give me 2. 0 minus 2 gives me -2. 4 minus 2 will give me 2. And -2 plus 0 will give me -2. Okay, so at the moment things are already starting to look fishy. Okay, so we have column 2 and column 3 looking identical. And if we look at column 4, column 4 is simply a multiple of column 3. Okay, so if we multiply column 3 by 2, it will look exactly like column 4. So already this is giving us some hints that at least 2 of these reactions are not independent. But let's continue with our Gaussian reduction just to get a definitive result. Okay, remember that I still want to aim for this form here. And currently I have a 1 here in this position and a 1 here, and I have my zeros, so that's looking fine. However, I need this 1 here to become a 0, and I need this 2 here to become a 0. So I'm going to leave these columns unchanged. Okay, column 1 and column 2. However, I am going to, in order to make this 1 here into a 0, I am going to subtract it from column 2. Okay, so that will be column 3 minus column 2. Okay, so that will be 1 minus 1, that's 0, minus 1, minus minus 1, so that's plus 1, so that's also 0. 1 minus 1, that will be a 0, minus 1, minus minus 1, and that's also 0. Okay, so the entire column seems to disappear. I only have zeros. If I look at column 4, okay, I want this 2 here to become a 0, so I need to add it to a multiple of column 2. So that will be 4 minus 2 times column 2. Okay, so let's do it. 2 plus minus 2 times 1 gives me 0. Minus 2 minus 2 times minus 1, that will also give me 0. 2 minus 2 times 1, that will give me 0. And minus 2 minus 2 times minus 1, that will give me 0 as well. So as you can see, columns 3 and 4 have disappeared, they've become 0. And this implies that my reaction 3 and 4 is independent. Sorry, is not independent. Okay, so reactions 3 and 4 is dependent. So now I know that the number of variables in other words, the number of reaction rates R1 and R2. So that will count for 2 independent variables instead of 4. Just as a side note, and you can perform this if you prefer as well, we can also perform a row reduction instead of a column reduction, and this will involve putting our reactions on the side here and our types of species at the bottom, or of course at the top, and listing them sideways instead of vertically. Okay, and we do our row reduction quite similar to the column reduction. And of course our aim will be to get this particular type of matrix where we have ones coming down diagonally and zeros underneath them. Okay, so it's important not to confuse them. This is in the case of row reduction. In the case of column reduction, we want a case where we have ones coming down diagonally and zeros above the ones. And note that if we do our row reduction for this same example, okay, we follow the same procedure and we end up with a matrix looking like this, with reactions 3 and 4 shown to be dependent. Okay, so back to our column reduction, which we have achieved. Now it is quite important for me to note that once we have done our Gaussian reduction, the reactions that we are left with will be the reactions that we are actually going to use. Okay, so it's not a simple case of choosing reactions 1 and 2 and discarding reactions 3 and 4. What Gaussian reduction does is it gives us a reaction set that is representative of our actual reaction set. Okay, so once we have done our Gaussian reduction, we need to rewrite our reactions. So let's look at what's left for reaction 1. Reaction 1 will be written as follows. So I have 2CO and 2H2 becoming CH4 and CO2. And in the case of column 2, well, in this case it remains pretty much the same. Okay, however, it is just column 1 that is reversed. So my actual reactions that I will be working with will have 2H2 plus 2CO becoming CH4 and CO2, and my reaction 2 will be CO plus H2O becoming CO2 and H2. Okay, so this is my final reaction set, and I can have an R1 and R2 associated with these reactions. Okay, in this particular example, my end reactions R1 and R2 looked very similar to reactions 1 and 2 here, but this is not always the case. So I suggest that you always work with the reactions that you are left with after your Gaussian reduction. Okay, so we're done with our Gaussian reduction and we have indeed just 2 independent reactions. Now we can proceed with our degree of freedom table. Okay, so let's look at our degree of freedom. Our number of independent variables. Okay, so let's count the number of species. I have 1, 2, 3, 4, 5, 6, 7, 8, and of course 2 reactions because this is a reactor. So that will be 8 plus 2. In terms of the number of balances, the maximum number of species associated with this reactor is 5. So that will be 5 balances. If we look at our specified compositions, remember that we are counting only independent compositions. So that's just 2. In terms of our subsidiary relations, we were given an H2 to CO ratio as well as a conversion. Okay, and that will bring our degree of freedom to 1. And recall that we were not given any flows, so we are at liberty to add a basis. So we can add a basis for just 100 moles per hour of feed, and that will bring our degree of freedom to 0. Okay, so now let's proceed with solving this problem. We can start either by writing out our balances or interpreting our subsidiary relations. Okay, in the case of our subsidiary relation, we have our conversion of 0.8, and that is equal to N1 of methane minus N2 of methane over N1 of methane. Using our basis, we know that our N1 of methane will be 50 moles per hour. So we can easily get our N2 of methane. And once we're done with that, we can write out our balances. Output is simply equal to input plus our production or consumption rate. Okay, and these are our balances. Okay, so for CH4, our methane, we have N2 of methane equal to our input N1 of methane, and our methane participates in reaction 1, my new reaction 1, and it's a product. So I'm going to add a plus 1 R1 here. That's of course equal to 10, so I can obtain R1 quite easily. The output of water is equal to the input, and it's being used as a reactant in reaction 2. So that's why we have 35 minus 1 times R2. In the case of CO2, the output of CO2 is equal to the input plus it is being produced in reaction 1 and reaction 2. So I have a plus 1 R1 and 1 R2. My CO here, there is no input of CO. However, it's being used up as a reactant, say minus 2R1 and minus 1R2. Okay, so note in this particular case, I have no input, yet I have CO being used as a reactant. Okay, so these reactions here, although I am using them, they are not necessarily the correct reaction, the actual reactions. The actual reactions that are occurring are the ones that were given to us in the original problem statement. So I'm working with the reduced reactions. They are not necessarily making any sense. However, they are valid and consistent from a material balance point of view, and that is what's important. That's what's relevant to us. Okay, so just be very rigorous about this. Write out the expression. We have our output is equal to input, and we have CO being used up. The same with the hydrogen as well. We have no hydrogen input, however, it's being used as a reactant in R1, and it's being produced in R2. So I have minus 2R1 plus R2. Okay, and from there, since I have R1, I can solve simultaneously, and I can obtain N2 of CO to be 50. And once I have obtained N2 of CO, I can obtain R2 and N2 of hydrogen. Okay, because I have the subsidiary relation. And ultimately I can get the species flow rate for the entire output stream. Once I have all of the species flow rates and of course the total flow rate, I can easily obtain the composition. And so this problem will be solved. So to summarize, let's look at our recommended strategy when solving material balance problems. Okay, first things first, read the question very carefully. Okay, so you have to read the question carefully in order to interpret all of the information that's given to you as well as the subsidiary relations. I recommend that you write all of your specifications on the diagram as they give it to you. Certain questions, they give you the specifications on the diagram. In other questions, they are simply stated in a paragraph format. But I suggest you write all of the specifications on the diagram, as well as the subsidiary relations. Okay, and take note of the species in each stream. And if this is not specified, then assume all species exist in an output stream, especially if a unit is a separator. Okay, sometimes we can also infer what's in a stream using a little common sense. Okay, if something is a separator and separation is stated to not be 100% efficient, then you will typically have all different products in all of your product streams, although at different concentrations. Okay, so take note of that. And also pay attention to reactors with specified conversion. If the conversion of a reactant is complete, then there will be none of that species in the output. Okay, so take note of all of this and write it on the diagram. Okay, this will be very helpful for you when you are performing your degree of freedom analysis. Okay, so once you've done with all of that, then you have to determine a set of independent reactions, okay, using matrix reduction. And if you are confronted with a problem with multiple reactors and different reaction sets, then you will have to do Gaussian reduction for each reaction set, okay, for each reactor. So it can become quite tedious, but it needs to be done. Okay, and once all of this is achieved, then you can commence with drawing up a degree of freedom table as normal. Okay, we've done this many times. Remember that for reactors, we are adding one independent variable for each independent reaction. We have to also add one subsidiary relation for any conversion that is stated, and also for the yield, right, the fractional yield. Okay, another problem to be wary of is if the problem simply states that the reaction goes to completion, it's necessary to find out which of the reactants is the limiting reactant. So you'll know which reactant reacted to completion. In other words, we'll have a zero output. Okay, and remember we've used this procedure. You simply find the smallest Ri, where Ri is equal to negative Ni in over Vi. And once you know what the smallest Ri is, you can figure out what the limiting reactant is. And if the problem states that conversion is whatever percentage, perhaps 70% or 80%, then you must assume that they are referring to the conversion of the limiting reactant. So if they don't state exactly what the conversion of which reactant is, you'll have to find out what the limiting reactant is. Okay, so in light of all of that, we can use our degree of freedom table to determine the best point to start our calculations and balances. Okay, remember for our separators, it's quite simple. Output is equal to input. For our reactors, output is equal to input plus our various production rates or consumption rates in different reactions for our particular species. Okay, and we of course need to use our subsidiary relations to complete the balancing or to solve the balances. Be wary that balances may be solved either sequentially or simultaneously. Okay, so there may be a case where you have enough information to sequentially solve your balances, whereas there may be cases where you'll need to solve for certain variables simultaneously. And if this becomes very complicated, you may find yourself having to put all of your species balances into a matrix and actually solving for your different variables. Okay, and it's quite easy thereafter. Total stream flows are obtained by adding species flows, of course, and stream compositions are obtained by dividing, okay, your particular species flow rate over the total flow rate. Okay, another thing that I failed to mention here, but I'll say it now, is that you have to also be wary of whether your information is being given in terms of mass fraction and mass flow rate as opposed to mole fraction and molar flow rate. It is particularly inconvenient to work with mass fractions and mass flow rates mainly because the reactions in a reacting system are expressed in terms of moles. So make sure you know how to convert between molar flows and mole fractions, mass flows and mass fractions.